A motor rated at 230 volts should work fine with 208 volts. The reason for this is that motors typically have a tolerance of plus or minus 10% around their rated voltage. This means that a 230 volt motor can safely operate with voltages between 207 volts, which is 230 volts minus 10%, and 253 volts, which is 230 volts plus 10%. Therefore, 208 volts falls within the acceptable voltage range for the motor. The voltage drop being experienced from 208 volts to 190 volts is likely due to the length and size of the wire. Number 12 wire is the minimum size required for a 2 horsepower motor running at 230 volts, but it may not be sufficient for the long run. By upgrading to number 10 wire, the voltage drop can be reduced and improve the motor's performance. The fact that the motor is overheating and shutting off after a few minutes of operation suggests that it is overloaded. This could be due to a number of factors, including too high voltage. Although 208 volts is within the acceptable range, too much load on the motor, poor ventilation or cooling around the motor, and bad bearings in the motor. To resolve the overheating issue, the following steps are recommended. Firstly, verify the load on the motor. Make sure that the blower and its fan are operating smoothly and not encountering excessive resistance. Secondly, ensure proper ventilation. Clear any obstructions around the motor and provide adequate airflow for cooling. Thirdly, inspect the bearings. Listen for any unusual noises or vibrations from the motor. If necessary, have a qualified technician inspect the bearings. Fourthly, upgrade the wire to number 10. Use number 10 THHN wire for the entire run from the panel to the motor. This will reduce voltage drop and improve the motor's performance. If the problem persists, contact a qualified electrician or heating, ventilation, and air conditioning technician to further troubleshoot the motor and blower system. It's important to understand motor voltage ratings and tolerances. Motors are designed to operate within a specific voltage range, and operating outside this range can lead to problems. Most motors have a nameplate that indicates the rated voltage and acceptable voltage range. Always check the motor's nameplate before connecting it to a power source. When a motor is rated for 230 volts, it typically has a tolerance of plus or minus 10%. This means the motor can operate safely between 207 volts and 253 volts. Operating a 230 volt motor on 208 volts is generally acceptable because it falls within the motor's voltage tolerance. However, it's crucial to consider the potential effects of voltage drop. Voltage drop occurs when the voltage at the motor terminals is lower than the voltage at the power source. This can happen due to the length and size of the wires connecting the motor to the power source. Excessive voltage drop can cause the motor to overheat, lose power, and eventually fail. To minimize voltage drop, use the appropriate wire size for the distance and current draw. The National Electrical Code, or NEC, provides guidelines for wire sizing based on the load and distance. For example, NEC Table 310.15b16 provides ampacities for various conductor sizes. Voltage drop can be calculated using Ohm's law, which states that voltage drop equals current multiplied by resistance. The resistance of the wire depends on its material, length, and cross-sectional area. Using larger wires with low resistance can reduce voltage drop. When troubleshooting motor problems, always check the voltage at the motor terminals under load. If the voltage is significantly lower than the rated voltage, investigate the cause of the voltage drop. In addition to voltage drop, other factors can contribute to motor overheating. Overload is a common cause of motor overheating. This occurs when the motor is drawing more current than it is designed to handle. Overload can be caused by excessive load on the motor, such as a jammed fan or a pump working against high pressure. Insufficient ventilation can also cause motor overheating. Motors generate heat during operation, and proper ventilation is necessary to dissipate this heat. Make sure the motor is not blocked by obstructions and that there is adequate airflow around the motor. Faulty motor components, such as bad bearings, can also cause overheating. Bad bearings create friction, which generates heat and can damage the motor. Listen for unusual noises or vibrations coming from the motor, which could indicate bad bearings. When troubleshooting a motor that is overheating, start by checking the voltage at the motor terminals under load. If the voltage is within the acceptable range, check for overload, insufficient ventilation, and faulty motor components. Upgrading the wire size can help reduce voltage drop and improve motor performance. Use number 10 THHN wire for the entire run from the panel to the motor. This will provide a lower resistance path for the current and reduce voltage drop. Also, ensure the connections are tight, because loose connections can cause resistance and lead to voltage drop as well. If the motor continues to overheat after addressing these issues, contact a qualified electrician or HVAC technician to further troubleshoot the motor and blower system. They can use specialized equipment to diagnose the problem and recommend the appropriate solution. Remember that electrical work can be dangerous, so always take precautions to protect yourself from electric shock. Turn off the power before working on any electrical equipment, and wear appropriate personal protective equipment, such as gloves and safety glasses. When working with electrical wiring, it's essential to follow the National Electrical Code and local electrical codes. These codes provide guidelines for safe wiring practices and help prevent electrical hazards. Always obtain the necessary permits and inspections for electrical work. This ensures that the work is done safely and in compliance with the applicable codes. If you are not comfortable working with electrical wiring, it's best to hire a qualified electrician. An electrician has the training and experience to safely and effectively perform electrical work. They can also help you troubleshoot electrical problems and ensure that your electrical system is operating safely and efficiently. Motors rated for 230 volts can typically operate on 208 volt systems, but it's important to consider the potential effects of voltage drop and other factors that can contribute to motor overheating. By following the troubleshooting steps outlined above, you can identify and resolve motor problems and ensure that your motor is operating safely and efficiently. Always consult with a qualified electrician or HVAC technician if you have any concerns about your motor or electrical system. Proper motor operation involves various aspects, starting with confirming the motor's suitability for the available voltage. While a 230 volt rated motor can function on a 208 volt supply due to a common plus or minus 10% tolerance, real-world conditions demand a closer look. Firstly, the actual voltage of the motor terminals needs to be assessed under load. A significant drop from the 208 volt source indicates wiring inadequacies. Secondly, wire gauge plays a crucial role. The provided scenario highlights a transition from metal-clad cable to PVC conduit with individual THHN conductors. While THHN is a robust insulation type, the wire gauge itself, initially number 12, might be insufficient for the 150-foot run, regardless of the transition. Thirdly, NEC guidelines, particularly Chapter 9 Table 9, detail conductor properties. This information alongside NEC Article 310.15 are critical for calculating voltage drop. The calculation considers conductor material, length, anticipated current draw based on the motor's horsepower and voltage, an allowable voltage drop percentage, generally not exceeding 3% for branch circuits. Fourthly, upgrading to number 10 wire offers improvement due to lower resistance per unit length. However, a comprehensive voltage drop calculation must validate its adequacy. Factors like ambient temperature and conduit fill, influencing ampacity, as outlined in NEC tables 310.15b16 and 310.15b3 should be considered. Fifthly, the motor's thermal overload protection is kicking in, implying an issue beyond simple voltage supply. It signals excessive current draw. This could be due to mechanical load, internal motor winding faults, or, as in this case, potentially low voltage exaggerating the current draw needed to meet the load demand. Sixthly, the blower itself warrants inspection. Restrictions in the blower assembly, such as debris accumulation or bearing failure, create mechanical overload, increasing motor current draw. Seventhly, motor terminal connections must be scrutinized. Loose connections increase resistance, generating heat and impacting voltage delivery. Oxidized or corroded connections exacerbate this problem. Eighthly, the local electrical inspector is a vital resource. They can offer interpretations of local codes and best practices, ensuring compliance and safety. Ninthly, consider the ambient temperature around the motor. High temperatures reduce motor efficiency and increase current draw, making proper ventilation essential. Tenthly, monitoring the motor's current draw with an ammeter while it's running provides valuable data. Comparing this reading to the motor's nameplate full load amps, or FLA, reveals if it's operating within its design limits. 11thly, the 2-pole toggle switch used as a disconnect needs assessment. Ensure it is rated for the motor's voltage and current. A switch with inadequate rating can create resistance and voltage drop. 12thly, the transition point from metal-clad cable to PVC conduit should be housed in a properly sized junction box. Wiring within the box should be neatly arranged and connections made with approved methods like wire nuts or terminal blocks. 13thly, ground fault protection is crucial. The motor circuit should have a properly sized ground wire extending from the panel to the motor, ensuring a safe path for fault current. 14thly, while the initial focus is voltage drop, consider the overall circuit protection. The breaker protecting the motor circuit must be appropriately sized to prevent nuisance tripping due to motor inrush current, while still providing overload and short circuit protection. 15thly, if the voltage drop remains excessive even after upgrading to number 10 wire, consider increasing the wire size further, for example to number 8, or exploring alternative wiring methods that minimize voltage drop. 16thly, if the motor continues to overheat, despite addressing voltage drop, load, and ventilation, internal motor issues become more probable. A motor repair shop can perform insulation resistance tests, surge tests, and winding resistance measurements to assess the motor's condition. 17thly, the use of a variable frequency drive, or VFD, to control the motor speed could offer benefits in specific applications. However, it requires careful consideration of motor compatibility and VFD programming. 18thly, regular preventative maintenance extends motor lifespan. This includes cleaning, lubrication of bearings if applicable, and periodic inspection of wiring and connections. 19thly, documenting all changes made to the motor circuit, including wire sizes, connection methods, and voltage and current measurements, aids future troubleshooting and maintenance. 20thly, remember that electrical work presents hazards. Always de-energize circuits before working on them, use appropriate personal protective equipment, and follow safe electrical practices. 21stly, regarding the option of rewiring the motor for 120 volts, this is generally not advisable in this scenario. While a 120 volt supply might be available, it would double the current draw, potentially exacerbating voltage drop issues and requiring even larger wire sizes. This is due to the power equation, power equals voltage times current. Therefore, for the same horsepower, lower voltage implies higher current. 22ndly, a 3-phase panel supplying single-phase 208 volts implies a corner-grounded delta or Y configuration. Understanding the panel's grounding scheme is essential for safe wiring practices. 23rdly, the distance from the panel to the time clock and then to the disconnect switch adds to the overall conductor length, contributing to voltage drop. Minimizing this distance where possible, or strategically locating the time clock closer to the motor can help. 24thly, if the blower is operating for extended periods, consider the motor's duty cycle rating. Intermittent duty motors are not designed for continuous operation and may overheat if run for too long. 25thly, reviewing the motor's service factor is important. The service factor indicates the motor's ability to handle brief overloads. A higher service factor provides a greater margin of safety. 26thly, the specific type of motor used in the spa blower, such as a capacitor-start induction run motor, has unique characteristics. Understanding these characteristics aids in troubleshooting. 27thly, ensure that all electrical components used in the spa area, including the motor, disconnect switch, and wiring, are rated for wet locations. 28thly, consider the use of a buck-boost transformer to increase the 208-volt supply to a more optimal voltage for the 230-volt motor. However, this adds cost and complexity. 29thly, the time clock controlling the motor should also be assessed. A faulty time clock can cause erratic motor operation and contribute to overheating. 30thly, remember that this is a spa blower in a hotel setting. Safety is paramount. Regular inspections and maintenance are crucial to prevent electrical hazards and ensure the well-being of guests. 31stly, consider the long-term cost implications. While upgrading wiring and components incurs an upfront expense, it can prevent costly motor failures and downtime in the future. 32ndly, proper documentation of the entire electrical system is essential for future maintenance and troubleshooting. This includes wiring diagrams, component specifications, and maintenance records. 33rdly, if unsure, consult with a qualified electrical engineer. Electrical engineers possess specialized knowledge in power systems and motor control, enabling them to provide expert guidance. 34thly, consider the impact of harmonics on the motor. Nonlinear loads in the electrical system can generate harmonics, which can cause motor overheating and premature failure. Harmonic filters may be necessary in certain situations. 35thly, always use properly sized conduit fittings and connectors. Undersized or damaged fittings can restrict wire movement and contribute to voltage drop. 36thly, when pulling wires through conduit, use a wire lubricant to reduce friction and prevent damage to the insulation. 37thly, after completing any electrical work, thoroughly test the circuit to ensure that it is operating safely and correctly. Use a multimeter to verify voltage, current, and continuity. 38thly, consider the use of a surge protector to protect the motor from voltage spikes. Voltage spikes can damage motor windings and shorten its lifespan. 39thly, ensure that the motor is properly grounded to prevent electrical shock hazards. A grounding conductor should be connected from the motor frame to the grounding system. 40thly, regular cleaning of the motor can help prevent overheating. Dust and debris can accumulate on the motor windings and restrict airflow. 41stly, if the motor is located in a corrosive environment, consider using a motor with a corrosion-resistant enclosure. 42ndly, if the motor is subject to frequent starts and stops, consider using a motor that is designed for frequent starts. Frequent starts can generate heat and shorten motor lifespan. 43rdly, consider the use of a soft starter to reduce inrush current during motor starting. Soft starters gradually increase the voltage applied to the motor, reducing stress on the electrical system. 44thly, ensure that the motor is properly aligned with the driven equipment. Misalignment can cause excessive vibration and wear on the motor bearings. 45thly, if the motor is used in a critical application, consider having a spare motor on hand. This will minimize downtime in the event of a motor failure. 46thly, consider the use of a motor monitoring system to track motor performance and detect potential problems early. Motor monitoring systems can provide valuable data on motor voltage, current, temperature, and vibration. 47thly, if the motor is located in a hazardous location, consider using a motor that is designed for hazardous locations. Hazardous location motors are designed to prevent explosions.